So let's see, where are we at? We're in section 7.4. We're going to talk about matrices and systems of equations. So first off, let's just the way our book defines a matrix. Our book says it's a rectangular array of real numbers. So that's a good enough definition for now. Matrix. There can be other things in matrices than real numbers. What we're going to do for now is use numbers in matrices. So when we're talking about a matrix, we're talking about, for now, a rectangular array of real numbers. But if you go further in math, you'll use matrices with lots of different things in them. We talk about and the numbers in the matrices are called the elements. And we refer to our elements in our matrices by the row and the column. And we use a subscript notation. So our element, and I'm going to use A for our element A, I, J. I tells what row it is in, and J tells what column it is in. So if we said, if we're talking about matrix A and we said A 2, 3, we'd be talking about the element in the second row, third column. We talk about the number of rows and the number of columns of a matrix is its dimension. So we refer to it as rows by columns. So a 2 by 3 matrix would have 2 rows, 3 columns. 3 by 3 matrix, 3 rows, 3 columns. A square matrix has the same number of rows and columns. We would say n by n. So a 3 by 3 matrix, 3 rows, 3 columns. And a row matrix would just be in a row. We're just getting some vocabulary out of the way here. So a row matrix would be something like this: A11, A12, A13, etc. And a column matrix would only have a column. So it would be A11, A21, A31, dot, dot, dot. So that would be a column matrix. And we'll eventually work with each kind. Let's see. So what we're going to do is take our systems of equations and we're going to translate them into matrices. So a matrix, when we turn our system of equations into a matrix, all we're doing is getting rid of the variables and we're just writing the coefficients, because that's really all we end up working with when we're solving systems of equations is the coefficients. So Let me write an example. It's really, the idea is really just a little change from the way we've been working with systems of equations, and everything else is exactly the same. So let's write one down. So what we're going to do again is we're going to take our system of equations and turn it into a matrix. So if we have the system 2x plus 3y minus z equals 4, x minus 2y plus 3z equals 8, and 3x plus z equals 5. So that's our system of equations. I'm just going to write our matrix just with the coefficients, just with the numbers. So I'm going to turn this into the matrix 2, 3, negative 1, 4, 1, negative 2, 3, 8, 3, and when I don't have a coefficient, I don't have a variable, I need to put in a 0 in there, 1, 5. Hello?
Could I finish that then?
Yes. So there's our system of equations translated into a matrix. Now if I were just to write the matrix of the coefficients on my variables, so if I just wrote the 2, 3, 1, 1, negative 2, 3, 3, 0, 1, if I just wrote that as a matrix, that would be the coefficient matrix. So if I just wrote this piece as a matrix, so if I just made that into a matrix, that would be the coefficient matrix. When I put the column of constants here on the end, and a lot of times you'll see it written with a dashed line in between, doesn't have to be there, helps you keep the two separate. If you write the coefficient matrix, but you put the column of constants on there, that whole thing together is called an augmented matrix. So we're augmenting our coefficient matrix with the constants there. And what we're going to do with our augmented matrix, we're going to take our system of equations, turn it into an augmented matrix, and then we're going to perform row operations on the matrix. So our row operations are exactly the same row operations. And that rings like one time a year. Our row operations are exactly the same as the row operations we use on a system of equations. So we're just going to translate our system of equation row operations to our matrix. We can exchange any two rows. So the things we can do are exchange two rows. So we don't like the order they're written in or whatever. Sometimes it's easier to work with a matrix after we change the position of two rows. So we can exchange two rows. We can replace any row. By its multiple. So we can basically what we're saying is we can multiply a row by any number and then replace that row with our result. And finally, the one that we use mostly to work with matrices is we can replace any row by the sum of itself and the multiple of any other row. So this is the process that we use in our system of equations, where we multiplied one row by something, multiplied another row by something else, and added them together and wrote what we got into our system of equations. That's what we're saying that we can do here. These are our three operations that we do, just like we did with systems of equations. Nothing different. They're exactly the same. Once we perform row operations, we end up with a matrix that we say is row equivalent. So after we perform our row operations, we end up with a row equivalent matrix. So the kind of the bottom line we're saying with these row operations, they don't change the result of what the matrix is telling us. So we end up with a row equivalent matrix. So what I want to do is we're going to do one example of turning a system of equations into an augmented matrix using row operations to solve our system of equations. That's really all we're doing today. Just translating our system of equations into the language of matrices. As we move on in Chapter 7, we're going to do some other things with matrices that let us kind of bypass the row operations a little bit. So working with the matrices in a little different way, but we want to be familiar with this process. So questions so far about what we're talking about? All right, so let's look at an example. So our system of equations is going to be x plus y plus 2z equals 3, 3x plus 4y plus 4z equals 9, and 5x plus 2y plus 15z equals 13. So there's our system of equations. We're going to write it as an augmented matrix. So I'm going to write my matrix 1, 1, 2, 3, 3, 4, 4, 9, 5, 2, 15, 13. So there's my augmented matrix. And you can put the dotted line there if you want. Now what we're going to do is do our row operations on this matrix. The idea here is, just like with a system of equations, I want to get these numbers to be zeros. So I'm going to use the first two rows to get this to 0, first and third row to get that to 0, and then whatever I'm left with, I use rows 2 and 3 to get that one to be 0. So what we do with these, the first row is not going to change. The only thing that would change the first row is if we multiplied it or divided it by something. But we don't have to change it, so I'm going to write 1, 1, 2, 3. And then what we normally do is write the operation that we're performing next to the row that we are replacing. So the first row we're going to replace is the second row. So what do I need to do to this first row so that I can add it to the second one to get rid of that 3? Like we did with systems of equations. How would I get rid of this 3 in a system of equations? Multiply the first row by -3 and add it to the second row. So I'm going to write here minus 3 R1 plus R2. That tells me what I'm doing to get this answer. So -3 times 1 is -3 plus 3, I get 0. -3 times this one, -3, plus 4 is 1. Negative 3 times 2 is negative 6, plus 4 is negative 2. Negative 3 times 3 is negative 9, plus 9 is 0. And now how are we going to get rid of that 5 in that first row using these row 1 and row 3? Negative 5 R1 plus R3. And one reason that you write these down is because it's very easy to make an arithmetic error or a subtraction error or something. So you write this so you know what you did to get your answer, so you can go back and backtrack. So we do negative 5 plus 5 is 0, negative 5 plus 2, negative 3, negative 10 plus 15 is 5, and negative 15 plus 13 is negative 2. So there's my new matrix. I got these two first elements here to 0. So this would be a row equivalent matrix to this one. Now we're going to use these two rows to get rid of this 3. So first two rows don't change now. 1, 1, 2, 3, 0, 1, negative 2, 0, 0, whoops. And now what are we going to do with these two rows to get rid of this negative 3? Multiply the top one by 3, so we're going to replace this by 3 R2 plus R3 from this matrix. So this is going to stay a 0. 3 times 1 is 3, minus 3 is 0. 3 times negative 2, negative 6, plus 5 is negative 1. And 3 times 0 is 3, minus 2, or sorry, 0 minus 2 is negative 2. So here's my another row equivalent matrix. I got these elements to 0. I'm going to do one more thing to this matrix just so I can explain or give you one more vocabulary word, just so you know. 1, 1, 2, 3, 0, 1, negative 2, 0, 0, 0, 1, 2. So what did I do to that last row to get rid of those negative signs? Multiplied by negative 1 minus R3. We call this matrix where we have zeros on this diagonal in the coefficient, or sorry, ones on the diagonal in the coefficient matrix and zeros below. This is reduced, or this is row echelon form. So this matrix would be in row echelon form, where you have ones on the diagonal here and zeros below the diagonal. We don't have to do that to come up with our solution, but I just wanted to tell you what row echelon form is. We could go one step further and get rid of these numbers above the diagonal also by doing our row operations. And if we have ones on the diagonal and zeros above and below my ones, that would be reduced row echelon form. We have zeros above and below. You don't have to do that. I'm not worried about doing that. It's kind of nice. It just adds some extra work. So if you have zeros above and below your ones here, then we call that reduced echelon form, or reduced row echelon form. All right, now we need to get our solution. We were trying to solve this system of equations. Well, now I'm going to rewrite this. I'm going to go back and rewrite this as a system of equations. So this tells me that my row equivalent system of equations is x plus y plus 2z equals 3. Y minus 2z equals 0 from this one. And from this last one, z equals 2. And now I can do back substitution. And when I do back substitution, I would find that y equals 4. I plug in 2 here. And then I plug in 2 and 4 into this equation, and I get x equals negative 5. And what we've done now with this matrix, this method, is Gaussian elimination with back substitution on this matrix. So we get a row equivalent matrix, turn it back into a system of equations, and then do our back substitution. So this process, again, is Gaussian elimination. So we're doing the exact same process that we did with a 3-variable system. We just write everything in terms of a matrix rather than in terms of a system of equations. So we just did Gaussian elimination with back substitution on this matrix. And our rules for how our answers come out are exactly the same. If you end up anywhere with something like 0 equals 1, 5 equals 7, you're going to have no solution. If you come up with something like 0 equals 0, you're going to have an infinite number of solutions. Just like with a system of equations. Nothing different. Questions here? Well, so the question is, what's the benefit of doing this way instead of a system? One, you don't have to write the variables, so it's a little cleaner. Two, matrix operations lend themselves a little more to a computer program, so that the computer can work with these kinds of things fairly easily. And then the other benefit is what we're eventually going to do is do some other operations with the matrices that let us kind of bypass these row operations. So we can do some other things with the matrix that we can't necessarily do with a system of equations that let us bypass doing all this stuff. Somewhere that this is going, yes. So questions on Gaussian elimination using matrices? Yeah, sure moves. All right. In one of your, I think on problem number 67 in the homework, I'll write the homework in just a second, but on number 67, it says use Gauss-Jordan elimination, and we can just use Gaussian elimination. Gauss-Jordan is when we get the reduced row echelon form. For number 67, just use Gaussian elimination. So let me I want to write the homework up, and then I have one question for you guys. I want to talk about one particular kind of problem. Page 13. And most of these are not solve the system using Gaussian elimination. They're asking other kinds of questions. So you're not having to do this whole process always. So don't worry. All right, there's the homework. Last class, most people finished before the end of class. So you shouldn't have homework tonight. So I have one question. What if we had a problem that said we have a parabola y equals ax squared plus bx plus c. So there's our parabola. And this parabola, and I'm just making this up, so I'm not even sure that the problem that I make up might not actually work out perfectly. But let's say it goes through some specific points. Let's say it goes through the point 1, 2, 3, 11, and 7, 20. So we have a parabola and it goes through those 3 points. And the problem asks us to find A, B, and C, given this information. What would we do? What do you think, Justin? So we're going to write this as a system of equations. Each of these is an x and a y. So for this set of numbers, I would have, for example, 2 equals a plus b plus c, because x equals 1. For this set of numbers, I would have 11 equals 9a plus 3b plus c. For this set of numbers, I would have 20 equals 49a plus 7b plus c. Then I have 3 equations, 3 unknowns, and then I can solve those with a system of equations. So the reason I'm telling you this, Mr. Leader really likes this kind of problem. So I want to make sure I mentioned it because Mr. Leader likes this kind. All right, questions? Oh, and you can find some examples of these. Let me find the page number here. The parabola problems. There's a couple of them. I just want to make sure you understood the idea. Well, you can find a couple. Let me find them for you. Page 501, number 77 and 79. So you can find examples of these kinds of problems there.